Magnetism. A magnet is made up of many tiny magnets called domains. When the domains are aligned in the same direction, you get a magnet. When the domains are randomly arranged, you get an unmagnetized material such as a piece of iron or steel. There are 4 ferromagnetic materials to remember for O-level: iron, steel, cobalt, and nickel, which means they show strong magnetic properties. Repulsion is the only sure test for a permanent magnet, because when 2 items attract each other, it can be between a magnet and a piece of iron, or it can be between a magnet and another magnet. So attraction doesn't tell us whether we have 2 magnets attracting each other or a magnet attracting a piece of iron. Magnetic field is defined as the region around the magnet where magnetic substances experience a magnetic force. A magnet suspended freely in the air comes to rest with the North Pole pointing towards the North Pole of the Earth, and the South Pole pointing towards the South Pole of the Earth. And that is because the North Pole of the Earth is actually a magnetic South Pole. On the other hand, the South Pole of the Earth is a magnetic North Pole. Like poles repel each other, unlike poles attract each other. Magnetic induction, or induced magnetism, is a process whereby a magnetic material such as a piece of iron or steel becomes magnetized when it is placed near or in contact with a magnet. So prior to bringing this piece of material close to the magnet, it is unmagnetized, but once placed near to the magnet, it becomes magnetized. So that is magnetic induction. Magnetic induction is temporary, so the induced magnet will lose its magnetism once the inducing force is removed. Magnetization. The first method of magnetization is using direct current or current flowing in the same direction. We use a coil of wire called a solenoid, and we pass a current through the solenoid to produce a magnetic field. And this magnetic field looks exactly like the magnetic field of a bar magnet. When placed inside the solenoid, the domains in the piece of iron will be aligned such that the North Poles will point in one direction and the South Poles point in the other direction. Thus, the piece of iron or steel becomes a magnet. Now, if it's a steel bar, the magnet produced is a permanent magnet. If it's an iron bar, then the magnet produced is a temporary magnet or an electromagnet. To determine the direction of the magnetic field, or to identify the poles of the magnet placed inside the solenoid, we need to learn the right hand grip rule. Imagine the 4 fingers curling towards the direction of flow of the current. Then the thumb points towards the North Pole. Second method of magnetization, stroking method. And there's a single touch method and a double touch method, but the idea or the principle is the same. The North Pole of the stroking magnet attracts the South Pole of the domain. We can use an arrow to represent the domain, with the arrowhead representing the North Pole and the other end representing the South Pole. So the stroking magnet's North Pole attracts the South Pole and pulls it to the right hand side. In this way, all the domains get pulled such that the South Pole is facing the right hand side and the North Pole faces the left hand side. The same thing happens in the double touch method. The South Pole of the stroking magnet attracts the North Pole and pulls it to the left side. In doing so, all the domains get aligned with the North Pole to the left. Similarly, the North Pole of the stroking magnet attracts the South Pole of the domain and pulls it to the right. Now, all the domains become aligned this way. We can use soft iron keepers to store magnets. The magnetic field flows from south to north inside the magnet and continues on to the keeper magnet. And in this way, the magnetic field flows continuously in a loop inside the four magnets and never gets lost to the surroundings. Demagnetization. The first method of demagnetization is by the use of an alternating current. An alternating current is one whereby the current changes direction many times per second, and as such the magnetic field direction will also change direction many times per second, and so the domains become flip-flopped left and right many times per second until their alignments get destroyed, and so the alignment becomes disorderly and randomly arranged, and thus the magnet loses its magnetism. The second method of demagnetization is by heating or hammering. The effect of heating or hammering is to cause the domains to vibrate more violently. They vibrate so violently that they break out of their aligned positions back to their original unaligned positions, which are randomly arranged such that the net magnetic field of the entire piece of iron or steel becomes zero, or rather goes back to zero. There are important usages for temporary magnets and permanent magnets. We use iron to make temporary magnets and steel to make permanent magnets because of their respective properties. Iron is characterized as soft, not because it's physically softer, but because, or rather not because it's very soft, but because it can be easily magnetized and easily demagnetized. Similarly, the steel is referred to as a hard magnetic material because it's difficult to magnetize and difficult to lose its magnetism. We can use the temporary magnet in a variety of situations. In a relay, to protect the home in situations of excessive high current, as a fire alarm, which is basically a bell and a doorbell. We also use permanent magnets in motors, dynamos, and generators. Worked example. we have three bar magnets: magnet X, magnet Y, and magnet Z. Magnet X attracts many iron nails. Magnet X also attracts many iron nails through a piece of iron, but magnet Z attracts only a couple of iron nails through plastic. First question: what happened to the iron placed under magnet Y? They experienced magnetic induction, so they became temporary magnets, so they can be attracted towards or to magnet X. Question B: magnet Y also attracts many iron nails. Why? Because iron is easily magnetized and can become a strong temporary magnet, and this strong temporary magnet can attract many iron nails. C: if you remove magnet Y, what happens after that? Because iron is a temporary magnet, it will lose its magnetism the moment magnet Y is removed. As a result, there will be no more magnetic field left in the iron. The iron will not be able to continue to attract the iron nails. The iron nails will fall off. Finally, D: plastic is non-magnetic, but there are still two iron nails attracted to it. Why? Because the magnetic field of magnet Z can flow through plastic to reach the iron nail. As a result, the iron nails can be magnetized by induction and become temporary magnets and can be attracted to magnet Z. The end.